Good afternoon. I am again here in this Basics of Remote Sensing and DIP module of EduSet program. In my last lecture, I talked about image classification, starting with what is image mathematically to correlate with matrix and vector. And then I talked about the separability analysis, which is very, very important for finding out the specific bands which are required to classify the image with very high accuracy and with the minimum number of processing time. Plus, I also then I started talking about the classification, definition of classification, supervised and unsupervised classification. And then I've talked about unsupervised classification initially. And then I also talked about supervised classification with two algorithms, which is minimum distance classifier and the Mahalanobis distance classifier. In my previous lecture, two algorithms of supervised classification were not covered. And here you can see it is listed, the algorithms. It is parallelopiped or called box classifier, and next is maximum likelihood classifier. So these two algorithms I will cover in today's lecture. I will also cover about the accuracy assessment of classified output. So if you look into, I talked about how we see the image. If we have a two-band image, we can plot the image in this feature space of 2 dimension. Here we are getting the band 1, and here on y-axis we are getting the band 2. So we may have a 2-dimensional image. This is your band 1. And this we can say band 1. And here I can say it is band 2. So using the pixel values, we can plot band 1 and band 2 in the feature space. So here we can say it is band 2. Now, since we are going for supervised classification, and if we already know that we are extracting water class, we are extracting agriculture class, so forth. So we should have the training data of these classes. If we talk about for water, we should image for class water, so sample 1, sample 2, sample 3, sample 4, and so forth. Suppose we take 10 samples, and here the value will come from band 1, suppose it is 10. For band 2, suppose it is 100. In second sample, the value may come 9 in band 1. In band 2, it can be suppose 100.01. Like this, the values may be coming up, just for example. Now, if we are applying the parallelopiped classifier, same way we can see the samples for agriculture also. Sample 1, sample 2, sample 3, sample 4, and so forth. Maybe 15 samples we are taking. So here for sample 1, the value can be 75. On band 1, value on band 2, it is 150. Again here band 1, it is 76, for example. It is 151, so forth. The values samples will in the sample, the value will be there. Now, if we are applying the parallelopiped classifier, this is also called box classifier. Box means we are creating the box of each class, and in that box, whatever pixels are there, these pixels are labeled to the class. Question comes how to create the box. To create the box, we can use two methods. One is using mean, and standard deviation. Second is we can use minimum and maximum parameters. See, all these parameters are statistical parameters. So these parameters we can generate from the training data of each class. We can get the mean value from here. And once we have mean and we have samples, we can calculate standard deviation, right? Second thing, we can also find out the minimum and maximum in each band. So in band 1, we can find out minimum and maximum. Same way for band 2, we can find out minimum and maximum from the given training data. If I'm talking about for water, so from this given training data of water, we can find out in band 1 minimum and maximum. Same way in band 2, we can find out minimum and maximum. When I'm talking about agriculture, in agriculture also we can find out in band 1 minimum maximum, in band 2 minimum and maximum. And if you are working with mean and standard deviation, so we can find out mean and standard deviation for agriculture class sample. And same way we can find out mean and standard deviation for class water. So if we start with minimum and maximum, here we can find out minimum and this is the maximum for class water. Same way on band 2, we can find out minimum and maximum for class water. Now, if I join these points like this, if you extend in the feature space, so here you will get a box. Now this box has been created using the training data of class water. So this box to be labeled as water. Now, if you plot all these pixels of this image here, whatever pixels are coming in this class water will be labeled to class water. Same way you can plot the box for agriculture using minimum maximum values from agriculture training data. So box may come like this. So whatever pixels are there in this box, these pixels will be labeled to class agriculture. So like this, you can go on creating the boxes for different classes using the training data of that class. And in that box, whatever pixels are there, these pixels are labeled to that class. If you are working with minimum and standard deviation method, so again, drawing the feature space of band 1 and band 2, B1 and B2. So you can create the mean on band 1 for class water. Then you have standard deviation for class 1, which is here minus sigma W and plus sigma W. Now mean you can find out on band 2 also for class water, X bar W. Then minus sigma W and here plus sigma W. Now using these sigma boundaries, if you extend like this, and if you extend from here, and if you extend from here, you got the box for class water because we have used the training parameter of water. So whatever pixels are there in this box, they will be labeled to class water. Same way you can create the box using mean and standard deviation for agriculture crop, and then class, and then you can whatever pixels comes in this box will be labeled to agriculture class. Like this, you can go on proceeding to label the different pixels for different classes while creating the box of that class using mean and standard deviation method or minimum and maximum method. So this is the box classifier, or also called parallel pipe classifier. In theory, it is a very quick process to classify, but in the book, it's also called, it's a very dirty process because you may not get very good results from the parallelepiped classifier. Next is maximum likelihood classifier. In short, it is called MLC. MLC. So this is a probability method. You have seen the previous distance equations, which were working on the minimum distance criteria. The distance should be minimized, but here it is working on probability, and the probability or the occurrence of that pixel for that class should be maximum. So how we can get the probability? You can see the formula for probability. P is equal to 1 upon 2 pi to the power n by 2. Then there is a mod of A inverse matrix. Then E to the power 0.5. Then there is a matrix here, xi, sorry, it is I basically. Xi minus x bar j, then transpose, then A inverse, and then again xi minus x bar j. So this is the formula where we can get the probability. I will explain all these parameters. Here small n is bands. Bands in image. Here A inverse is a weight matrix. It can be unit matrix, variance covariance matrix, or diagonal variance covariance matrix. Xi is unknown pixel, and x bar j is mean of a class. I'm using mouse, so my writing is not coming. Let me just write it a little better. Class. So the xj bar is the mean of a class. So this we are calculating mean from the training data of each class. Xi is an unknown pixel vector coming from the image. A inverse is a weight matrix. It has 3 norms, either unit matrix, either variance covariance matrix, or diagonal variance covariance matrix. We can take the unit matrix, or we can take diagonal. We can take the variance covariance matrix also. If we are taking unit matrix, we know the unit matrix. Once we know the image in the bands are 3 bands, so we can have here 3 by 3 unit matrix like this: 1 0 0 0 1 0 0 0 1. So here we can get the unit matrix. If you are taking variance covariance, again it will be 3 by 3. If my image is 3-dimensional, 3 bands, so variance covariance we can get from the training data. In my previous lecture, I have written the formula how to do it in detail. I'm not covering here. From this training data of each class, we can get the variance covariance matrix of each class. For water, we should have one variance covariance matrix, and for agriculture, we should have again one more variance covariance matrix. The formula I can write, suppose if we have 3 bands, my A inverse will come like R11, R12, R13, R21, R22, R23, R31, R32, and R33. So how to get this element, since it is coming 3 into 3, here n is equal to 3. So how to calculate here? R I j can calculate by summation xi minus x bar, and then here yi minus yi bar divided by n into n minus 1, where here n is number of samples in training data, right? So like this, you can calculate the elements of variance covariance matrix, and then you can use it. Here, this T is a transpose because it is a vector difference of between xi and xj bar. Once you have a matrix of one dimensional, you can take it transpose, it will come like this. And then this is A inverse, and this is the vector difference again between xi and xj bar. The dimension T of this matrix, it will be 1 into n here. This will be n into n, and this will be n into 1. Then only you can multiply, because this is same, then you can multiply, and here it will be same, then you again you can multiply. That way you can get the probability. So if you're expecting, suppose 2 classes, and you get the probability of water and you get the probability of agriculture for same pixel, here again you can draw B1 band axis and B2. You can plot the x bar j here, and for suppose this, you can give the name water, and this is for agriculture. So if this pixel to be labeled, you find out here P1W, and you find out here P1 agriculture. One means first pixel, and for water and for agriculture. If here P1W is more than P1 agriculture, so this pixel will be labeled to class water. Maximize, the probability should be maximum. So like this, the maximum likelihood classifier or MLC works with the criteria of the probability should be maximum. So this way, I talked about the supervised classification, where we require the training data. And from the training data, what we do, we calculate the training parameters. It can be mean, it can be minimum, maximum, it can be variance covariance, it can be standard deviation, and so forth. Once these parameters are calculated, that algorithm is ready to calculate the criteria parameter. It can be distance method using the Euclidean distance or Mahalanobis distance. In Euclidean distance, we use only mean parameter. In Mahalanobis distance, we calculate mean and variance covariance. In both the cases, the distance should be minimum. The third algorithm, parallel pipe, there it works with 2 methods, either with mean and standard deviation or minimum and maximum. All these parameters we can calculate from each class training data, and then we can create the boxes in the feature space, and whatever pixels comes in that box, they are labeled to that class. Third was, the fourth one was maximum likelihood classifier, where we have to calculate the probability using this formula, and then the probability should be maximized. And once we get the maximum probability, that pixel is labeled to that class. Now coming to next is accuracy assessment. So once we have the classified output, the objective of classified output is to get the thematic map of an area. Thematic map means we want to map the water bodies, we want to map the forest cover, we want to map the agricultural land with crop, without crop, we want to map the barren land, we want to map the built up area in that thematic map. So all these classes are present. So once we get the thematic map as a single layer, we want to check its accuracy. What is the classification accuracy? So for that, there are standard method. We have to create the confusion matrix or error matrix. So we require confusion matrix or error matrix. So what is required in this matrix? We require two map. One is the classified map, which we have already classified using the algorithms which I talked about. So like this, it may have the class water, it may have the class agriculture, it may have the class forest. So it is a classified map. Then second map is the reference map, which is generated from the ground truth data. And we know the water is coming like this in the ground, and agriculture is coming like this, and forest is coming like this. We can go to ground and we can create the reference sample points, and we can create the reference map, or we can use the some previously mapped map has been generated by somebody with very good accuracy that can be used as a reference map. Now here we can see in our classified map, we have three classes: water, agriculture, and forest. So we require a 3x3 matrix, that is called error matrix. So like this, we can create a matrix of 3x3. Oh, I've created more boxes. Okay, I can eliminate 1, 2, 3. This I can eliminate. And this I can eliminate. 1, 2, 3. This will work. I require this. 1, 2, and 3. So here, this side, you will see it is a reference. It is talking about this side. It is classified. And here you have to put the class name water, agriculture, forest, water, agriculture, forest. Here there will be row total. And here it will be column total. Now, how to fill this matrix, because this matrix is an empty matrix, and I will just create a boundary where you can see up to where the matrix is existing. So matrix is coming here 3x3 matrix, because we have three classes. The green boundary is the matrix range. How to fill the value? Suppose randomly or by stratified random, we take one sample. The sample comes here. Its geolocation is here, and the same sample location in the classified map is here. On the reference map is here. So in classified, that sample is water, and in the reference map is water. So here in classified it is water, and in reference map it is water, so it will come here 1. Second sample you take, it comes here. In classified it is water, and in reference it is coming agriculture. So here if you see classified, it is coming water, and in reference it is coming agriculture. So it will come here. I'm just telling you how to create the matrix with respect to the testing samples. So here we have to use testing samples. And using this testing samples, we can fill this error matrix. So we take the third sample. Suppose here it is forest, and here also it is forest at the same location. So this side is forest, and this side is again forest and forest. So it is coming here. Then we take fourth sample. It is coming here to be forest in the classified, and the coming agriculture. So here if you see classified is forest and reference is agriculture, it comes here. So like this you go on creating the samples, testing samples, and fill this matrix. So once the matrix is filled, you can see I have already created a ready-made matrix. The matrix looks like this. So here you calculate the row total, and here you calculate the column total. So here you can see 35, 10 and 5, it is 50. 2 plus 37 plus 1 is 40. Then 2 plus 3 plus 41 is 46. Here you see 35 plus 2 plus 2 is 39. 10 plus 37 plus 3 is coming to be 50. 5 plus 1 plus 41 is 47. Now if you total this one, or if you total this one, it will come equally 136. And this is basically total number of samples used, total number of testing samples. Testing samples. Right. And if you do interpretation, if you take these diagonal elements here, so these are the samples which are correctly identified on classified map, that is thematic map, and correctly identified on ground truth or reference data. This is your reference. Ground truth or reference, and here it is your classified map. Now once this error matrix is ready, we can create or generate some of the parameters like user accuracy. User accuracy means how correctly the samples are identified on classified map. How correctly the testing samples has been identified on classified map. And here for each class, we can get the user accuracy. Like for B class, the user accuracy is 37, correctly identified on thematic map and correctly identified on the classified map. So it is 37. And if you see its row total was 50. That means these samples were tested on the thematic map and they were 50. And out of 50, only 37 were correctly identified on thematic map. So its accuracy, user accuracy will be 37 divided by 50 into 100. It will be 74%. And if you differentiate, if you calculate 100 minus 74, that will give you error of commission. That means how many percentage of samples were wrongly identified on the thematic map, that is 26%. Next is producer accuracy. Producer accuracy means how correctly the samples are identified on reference map. So here you have to take again for class B. Now user accuracy and producer accuracy you can get for each class. You have to calculate for each class. For here, for example, I'm talking about accuracy of producer accuracy of class B. So here, if you see again, 37 samples were correctly identified on the classified map, and for class B, and correctly identified these same samples on class on reference map also, and that is 37. But total number of samples, if you see identified on the reference map for class B were 40. So accuracy, the producer accuracy for class B will be 37 divided by 40 multiplied by 100, it is 93%. And for this accuracy, you can also find out error of omission, that is 7%. So here, for each class, you can get the user accuracy and producer accuracy. Again, I'm repeating, user accuracy is how correctly the testing samples has been identified on thematic map. Producer accuracy means how correctly the samples are identified on reference map, right? And its accuracy you can represent by user accuracy and producer accuracy. You have to calculate for each class. So here you have 3 classes. So you should have 3 user accuracies for class A, B, and C. And also you can calculate error of commission for A, B, and C. Same way for producer accuracy, you will get for 3 classes, that is for A, B, and C. You can calculate the producer accuracy, and then also you can calculate the error of omission. Coming to next parameter, what we can calculate from this error matrix is overall accuracy. So overall accuracy means total number of testing samples and here you have to take sum of correctly identified testing samples. I'm writing in short, testing samples multiplied by 100. So here overall accuracy you may get, if you see your previous table which I've shown here, the total number of testing samples were 136. So here this will be 136. And here you see the sum of correctly testing samples. So here if you see here, it is for each class, it is 35 plus 37 plus 41. They are correctly identified on reference map and they are correctly identified on thematic map. So here you have to go for sum of 35, 37 and 41. So here 35 plus 37 plus 41 multiplied by 100, and we can calculate its value. If you take 35 so it comes to be 35 plus 37 plus 41. It comes to be 113 divided by 136 multiplied by 100. And you can now calculate overall accuracy in percentage. It comes to be 83.08%. Next is kappa coefficient. So fourth parameter what we can calculate is kappa coefficient. Why we have to calculate kappa coefficient? It is also called KHAT. K-H-A-T. And it is represented like A with a small cap or reverse V. cart. Because here this overall accuracy is using only the diagonal elements. It is not using off diagonal elements, and it cannot give you very good representation of your accuracy assessment. In that case, people have developed the kappa coefficient, which takes care the diagonal elements as well as off diagonal elements also. So here this n is total number of samples, that is 136. XKK is the samples, testing samples identified correctly on thematic map as well as on the reference map, and it is summation. So you have to go for summation of this one, diagonal elements. Then here this summation is a multiple of row with column total of each class. That means xk plus into x plus k. That means you have to multiply row total of class A with column total of class A plus row total of class B into column total of class B plus row total of class C into column total of class C. That way you will get this one. And if you put all these values in this formula, you can calculate the kappa coefficient. Its value is from 0 to 1. It is not in percentage. Its value comes 0 to 1. So here we can see how we can calculate this kappa estimates or kappa coefficient. It will be a little lengthy one. So here n is 136. Then summation, there was there summation xkk. K is nothing. It is basically 35 diagonal element summation. 35 plus 37 plus 41, which will come 113. We have already calculated. And then summation k and then x k plus into x plus k. So this is the summation of your row with column to be multiplied. So let's see, in the first case for class A, it is 39 into 50. 39 into 50 plus 50 into 40. 50 into 40 plus for third class, it is 47 into 46. 47 into 46. Now let's multiply this, how much it comes, and sum also. First we will multiply. So it is 39 into 50. It is 1950 plus 50 into 40. It is 2000. And again plus 47 into 46. 47 into 46. 2162. 2162. And let's do its sum total. So sum total is coming this one plus 2000 and plus 1950. It is coming 6112. 6112. Now we can put all these values in the formula. So formula for kappa coefficient, I'm not writing the formula. So I'm just writing n, that was 136, into diagonal sum. It was 113. Then it was minus with row and column total. That came 6112, 6112. And if you see the previous, it is n square. So here n square, you can in diagonal, n square is the total number of samples square, 136, minus row with column to multiple, or with the summation of row with, when we are multiplying corresponding class row with column total and summing up, the value is coming already, we have calculated 6112. Now we can calculate this value, 136 into 113. It is 15368 minus 6112 divided by 136 into 136. Sorry, 136. It is coming 18496 minus 6112. And now we can calculate its value. 6112. It is coming to be 12,384, and in numerator it is coming 15368 minus 6112. It is coming 9256. And this one, you can say how much cart is coming. It is coming to be divided by 1, 2, 3, 8, 4. 9256 divided by 1, 2, 3, 8, 4. So it is coming here 0.74. I'm just considering up to 2 decimals. So it is like this. It is not in percentage. This will be in decimals only, 0 to 1 value. So this is kappa coefficient. Overall, if you see, when kappa is more than say around 80, it is called very good classification, right? And when it is going, say 60, rather not 60, it will be coming, say 70 to 80, it is good. 55, rather you can take maybe 60 to 55 to 70, it is fair. And if it is less than 50 or less than 55, it is poor. So like this, the very broad range of accuracy can be calculated. Same way, this basically in points, not in 70 to 80, because this is in decimals. But same way you can calculate, you can see, do the assessment for the overall accuracy also. It is very good, or it is good, fair, or poor. So this way, from this error matrix, we can calculate 4 or 5 parameters, starting with user accuracy, that depicts how correctly your testing samples are on the classified map. Producer accuracy, how correctly your testing samples are on the reference map. Overall accuracy, while considering only the diagonal elements. And if you want off diagonal elements also, you can go for kappa coefficient or kappa estimate. And then by this formula, you can calculate the kappa coefficient, which is considering the diagonal and off diagonal elements. So as the number of classes are more, your this dimension of ABC in the matrix will increase. If you have 10 classes, your matrix will be, this error matrix or confusion matrix will be 10 by 10 size. In IIRS, it is called error matrix. In some softwares, it is also called confusion matrix. Maybe in NV or ILVIS, there they call this matrix to be confusion matrix. But in IIRS, it is called error matrix. So there are different terminologies in the different commercial softwares, but things are same, and you can calculate this matrix. I will in the syllabus it is not there, but I would like to mention, and you can go through in the internet using the YouTube channels, finding out how to get F score. F score, and then recall and precision. So these are the three parameters. Nowadays, people are more looking to calculate or represent the accuracy of your thematic map in the form of F score, recall, and precision. From the same matrix, you can calculate recall, you can calculate precision, and then you can calculate the F score, because F score is a function of recall and precision. So how this is done, you can go through in the YouTube channel, and there you can just read how people are doing it for F score and recall and precision. So overall, today what I've covered, I just started today from the previous lecture where I talked about separability analysis, supervised classification, unsupervised classification, and the algorithms for unsupervised classification, mainly the C-means algorithm. I talked mathematically how it works without training data, because it is unsupervised. That's also called clustering approach. And in the previous lecture, I also talked about the two supervised algorithm, that is minimum distance criteria using Euclidean distance and the Mahalanobis distance using mean and variance parameter. And today I started from the same point. I just linked what was covered in the previous lecture, and then I took the two supervised algorithms, that is your parallelopiped or box classifier and the maximum likelihood classifier. In the box classifier or parallelopiped classifier, we calculate the mean and standard deviation. That is one method from the training data of each class, or we calculate minimum and maximum parameter from each training data, and then we create the box, and in that box, whatever pixels are there, they are labeled to the class. It is just like we have a net, and we are catching the fish. In the net, whatever fish comes, they are labeled to that class. The next was maximum likelihood classifier, or in short, it's called MLC. This algorithm works on probability parameter, and I've given you the mathematical expression of it, how to calculate the probability by this method. And I also explained to calculate here all the parameters, mainly the variance covariance matrix. Then I went to the accuracy assessment part, and I here created mentioned what is required to go for accuracy assessment of a thematic map. We require a classified map whose accuracy to be checked, and we require a reference data from the ground truth in the form of map. And these two maps are required to create the error matrix. So that also I explained how to get the values in the error matrix using the testing samples. And then once the error matrix is ready, we can calculate the few parameters like user accuracy of each class with the error of commission, and the producer accuracy of each class and error of omission. These are all in percentage. We can calculate the overall accuracy from this matrix, and then we can also calculate the kappa coefficient. The kappa coefficient value is from 0 to 1. One more thing I would like to tell you, that testing samples and the training sample, what should be the size of training sample and what should be the size of testing samples. For training samples, The size, we can keep it, suppose one of the rule told by Jensen as 10n, where n is number of bands. But as you learn more algorithms for classification and for prediction, the requirement of training data is not following this rule. Sometimes some algorithm require very large training data, like if you talk about artificial neural network, they require large training data. But if you talk about the fuzzy classifiers, they require very small training data. And second is testing samples size. So for testing sample size, if you see the one of the thumb rule by Congleton 1991, he proposed that we should have 75 to 100 samples per class. So these are the rules we can follow when we are basically generating the training samples and testing samples. So this also gives the output or idea when you go to ground to collect the ground truth samples to be used as training and testing samples. You should collect the large number of training and testing samples. Nowadays, through mobile phone, there are very good apps. You can use it, and with that apps, you can get the GPS or GNSS coordinates, and you can geotag any sample, like some building or a water body or a forest patch or some fields of agriculture with crop, without crop. You can geotag them with the GNSS coordinates, so that you can overlay these coordinates on the image, and you can find out where are these samples lying on the image. And you can also overlay these points on the Google Earth, and you can easily understand how these samples are looking on the image. That gives you more understanding about how these samples are there on the image, so that you can really transfer these samples on your own satellite image, which you are processing for classification. So this is all about my today's lecture, where I talked about classification to accuracy assessment. Thank you all. And now